Welcome back to Gabversity, where facts certainly don't care about your feelings. And now we put on the brightness and we say hello to everybody. So here is the question that I thought we would start with, and I may have done some other ones before. I'll start with an easy one, which I may have deleted. Let me go back to where we were. And where are my flashcards and questions? There we go. So, hey, there's everybody's appeared straight away. So lovely to see everybody. So we'll start with the easy one. The easy one is as follows. How to calculate escape velocity. Hey, Two-Tank Frank! Long time, welcome back. Welcome back, my friend. We are doing some calculations. So we want to calculate the escape velocity from the surface from a typical neutron star. Okay? And we have to assume that the star has 1.4 solar masses. So it's 1.4 times the mass of the sun. That's what's up. With a radius of 12 kilometers. What's that? 6A. It's about 7.6 miles. So we do it in, that's the same equation. 12 kilometers. All right. What is the escape velocity? Now the escape velocity is quite gigantic. It means you could probably not get off it. You'd be crushed into dust. All right. So how's the equation work? Here is the equation. The equation is right there. 2gm over r, and you square root that. Hey, Kevborn, how did you go on your assignment? You didn't send me the messages. And you had an exam on, I think it was something to do with measuring with percentages and statistics, standard deviations, and calculating propagation of errors or something. Anyway, good to have you back, my friend. So the formula to calculate escape velocity is 2gm over r, and then you square root that. So what you do is you go into Excel, right, and now let's make a new spreadsheet. Not so good. I'm sorry to hear that, my friend. Well, we'll do more practice. Most people don't do well with errors, by the way. Even at university, I had to teach like the other people on errors, because the easiest way to do it is you convert it to percentages. And then you add up all the percentages along the way, and then you convert it back. I should do a scope on that one day when I'm not so busy. So we know that sprinkles and booze. So what we do, we know the formula is, I'll write the formula down for you guys. Okay, where's the pencil? Give me a pencil. Oh my God. All right, here it is. So the formula is right here. Hello. All right. Smart enough for these guys, but here I am. My dear, you love to play yourself down. I love your company. Always. It's always better when you're here. So we want, that's an E, by the way. That's a really bad version of E. Hey. All right, so escape velocity. Why did 9.8 meters per second squared pop up in my head? Good question. That is the acceleration of gravity on Earth, which is not, it's partially related to this. But that's a slightly different topic, but good question. All right, this is the gravitational constant. This constant does not change in our universe at all. And I think it's 6.674 by 10 to the minus 11, I think. I have no idea why I'm getting error percentages above 10%. All right. Well, I'd have to see an example question, I think, to be able to answer you properly. But if I go here, just type in G equals, and we should get it somewhere here. No, damn it. G constant. Let me just type in constant. Sorry, trying to do 5 things at once. Where is it? What is the value of G? What is the constant G? Give me a break. It's freaking so difficult to find. All right. I just want the constant. There it is. 6.673 by 10 to the minus 11. Excellent. That's what we thought it was. All right. So, as we said, G always equals the G. Capital G always equals 6.6 approximately. 6 by 10 to the minus 11. And the units are meters per kilogram all squared, which is... there should be a Newton in there somewhere. Yeah, there should be a Newton. It should be Newton meters. Yeah, there we go. Right, that makes more sense. So what, come on, you can do it. There we go. 6.6 by 10 to the minus 11. So we take this dot and we move it this way and we go 10 times, so 11 times. So there's 10 zeros in front of this 6. That's how small that number is. But that G in this universe does not change. It is always this number. Sprinkles and boozers back again. So we know the mass, right? The mass is 1.4 by the mass of the sun. And we know G and we know R. So all we have to do is just go in. They gave it to us. So they said R is 12 kilometers. So 12, hey, posh whisperer. So 12 kilometers is 12,000 meters. And 12, it's about 7.6 miles roughly, but we converted to 12,000 meters, which should be around the 38,000 feet roughly. And then 1.4 solar masses, which is 1.4 multiplied by the mass of the sun. So all we have to do is type in mass of sun. And Google should auto-complete it. There it is, mass of sun. 1.989 by 10 to the 30 kilograms. Can you figure out the equation that gets me back to my planet? When I figure out how to get there, I will bring you with me. By 1.989 times 10 to the 30. I remembered you the other day because Dr. Peterson was saying to stay in a healthy relationship, you've got to have a date with your partner at least once or twice a week. And I thought, fingers crossed, when you and Byron get married, you keep your dates up. And that's not a dirty joke. All right. So it turns out that's the equation. So all you have to do is get 2 multiplied, we are forever. That's awesome. I love hearing that. 2 times gravitational constant times the mass of the sun, right, or the mass of the neutron star, which is basically a sun compressed to the size of Manhattan, right? I think it's like a quarter of the Manhattan block or something, Manhattan Island. If you compress a sun into that, then the escape velocity becomes 1.76 by 10 to the 5 kilometers per second. Now, I'll tell you how much that is, because that is a ridiculous number. 1.76 by 10 to the 5. What the hell is that? Let me write that down. 1.76 by 10 to the 5. That's 176. 1, 2, 3, 4, 5. So that is 176,000 kilometers per second, right? And also per second, so 100 per hour, that's going to be 176,000 multiplied by 60 seconds in a minute times 60 seconds in an hour. 633,600,000 kilometers per hour. Now that in miles divided by 1.6. All right, so if you want to escape from a neutron star, you have to travel at 396 million miles per hour to escape from the gravity pull of a neutron star. In other words, you would be ripped to the shite house, my friends. Yeah. Just on a quick side note, there's a news update. Hezbollah kidnapped 6 ISIS people and returned them to get back Lebanese soldiers that had been held hostage by ISIS for the last 3 years. I think 7 or 8 of them came back dead and 1 came back alive. That's a badass speed, yeah. So that's just some update I just heard off Arabic news. Thought I'd share that with you guys. Unrelated to astronomy. Hemi. Yeah, that's... I just realized what you were saying. You too, Tank Frank. Always a pleasure, man. Anytime. So yeah, you'd have to use neutron fuel to get off. Jeez. Can you imagine having a Hemi like that? That would be awesome. No one would catch you. It's too funny. Anyway, so the book launch, man. I can't wait to talk to you guys about that because I had to sell the car to cover the book launch, but I'm pretty sure I'm getting a badass motorbike. Do you guys want to see the motorbike I'm probably getting? Because I had to, hey, just being Jen. Let me show you the motorbike that I'm getting. This actually was my bike years ago. I had to sell it to cover the launch. Yeah, I explained it on Gab Life. It was a live scope a couple of years ago. RSV 1000, 2005. The Great Space Coaster, that's the one. I will show you my bike, my friends. This is actually it's a very long story. My bike smashed. I bought another one in Lebanon brought the parts to Australia, rebuilt it, someone else smashed it, then they sold it. I've still got the car, it's up for sale now, so I can cover the book launch. Here is the bike, by the way, that I'm getting. There she is. This is a V-twin, 160, 140 horsepower. You rebuy your whole life. You know the feeling. So there she is. This was my original, but it got smashed, so that was my original. And then because it got smashed, I went to Lebanon and I bought this one. And you're not allowed to bring these into Australia, so I had to bring it by parts and then put the parts on this bike. So now this bike looked like that. And then some guy smashed it again. So then it looks like a Ducati. It's an Aprilia. Yeah, it wasn't me. It wasn't me that smashed it. I used to have a motorbike hire company, so I had like 15 motorbikes and 15 cars, and I would rent them out, and people would smash them. And people always smash that bike because people don't know how to ride a V-twin. Because V-twins have torque, man. They have torque like I don't know, like a horse that did a fart with jet fuel. Yeah. They do it every time they come in. They've never ridden, and we always tell them, you got to be careful. You can't do. Yeah. I know how to ride a bike. One guy rented the bike, went out the driveway, right, and smashed the bike in the driveway, right. He wrote the bike off. So that was the guy. That was the last guy who smashed it. He writes off the bike, and then he tries to sue me for saying, "Oh, you gave me a bike that's too powerful." I'm like, mate, you're actually wanting to admit publicly that you're a moron. Like, so go ahead, man. Horse farts are probably deadly without jet fuel. I would. Probably. Anyway, moving back to astronomy. So we've now solved that one. So here we come to the next question. So I spent 45 minutes working on this question. I'd be embarrassed to sue. I know. That's what I thought. I'm like, man, aren't you embarrassed? Anyway, so the company got shut down for other reasons. I won't get into it. And then bike got auctioned off to some guy, and then he fixed it and rode it around for 2 years, and then he put it up for sale. Now, my brother, in the meantime, had his own motorbike hire business, and he ended up having 30 or 40 bikes, and he's now an instructor and stuff. So he found the bike, and he went and bought it to get it back for the gabs. How awesome is my brother? So that was pretty cool. So now my brother's had it for the last 3 years, and I've ridden it once, but I won't ride it because it's his bike. I don't want to ride it. But anyway, I might get it off him now, so we'll see. All right, so if a nebula, that's the story of the bike. If a nebula, does anyone know what a nebula is, by the way? A nebula is sort of the birthplace of a star, I guess you could say that, right? It's a lot of gas everywhere before it's condensed into turning into a star and a solar system and stuff like that. So we have a nebula that in diameter is 6 light years. That means that if you send a message from one end of the nebula, it's going to take 6 years before the other people receive it. You want to be born where a star was born. You can see them all the time in space forming. It's so beautiful. I tell you, like, if anyone's been to my Instagram, Sunago, Elare, I hope I'm getting that right. I'm pretty sure you have Greek background. I keep speaking to you in Greek. If you go to my Instagram, I think it's Real Gabsmack. I took photos of the moon and the sun in the telescope. Yeah. And what you don't see in the photo is that when you're looking at it live with the telescope, you see the moon rotating. You actually see the moon rotating. And I saw Saturn shimmering, and I saw the sun spewing out hundreds of thousands. No Greek, I can study Greek, sorry. Yes, you are an intellectual man from memory. It looks amazing. So anyway, so you get to see nebulae, you get to see a star being born. You know, when the gas condenses, then it ignites, and then it just blows away. It's so beautiful. You've got to, if you ever do something in your life, you've got to go to an observatory. The Planet X theory. Oh, there's probably millions of Planet X's. Space is awesome. It's fascinating, absolutely fascinating. Real Gab smacked with an ED at the end. That's unicorn farts. Yeah, unicorn farts. Anyway, so if a nebula is 6 light years Nibiru in diameter and is expanding at a velocity of 11 kilometers per second, right? Which I think is the escape velocity of the Earth, if I remember correctly. Typical of planetary nebulae. How old is it? All right. So if a nebula is 6 light years in diameter okay? And it's expanding at a velocity of 11 kilometers per second. How old is it? So this was the equation that I created. I wanted to show you guys how I created this equation. So what I did was, I got the diameter, future child nebula. That would be pretty cool. Oh, she'd be gorgeous anyway. You may as well, because she'd be a mix of you and Byron. So she'd be like a glamour. Yeah, call her Nebula. And then all the guys will be writing love notes to her, like in 2050 or something. All right. So what I did was I put in Excel the light years. I put in the expansion rate. Hello. All right. And then I dropped Parendome a message. He's having a difficult time with his treatment. Okay. I sent him a message a week ago. I didn't hear from him, so I'll send another message to him, definitely. Yeah, I had a friend of mine who went through chemo, and I can't understand how hard that is, honestly. You know, it's crazy. All right, so I'll show you what I did. Don't thank me, man. Thank you for telling me. So here is the light. This is one line, right? So what I was trying to do. So this is a very, very basic mathematical modeling. Now I did this for fun because I didn't want to look up the equation. So I still don't know the equation that they give you. I wanted to make my own equation. Right, so what I did was I got a sample of answers and I tried to figure out a pattern, okay? And the pattern is in 2 dimensions. It's a 2-dimensional pattern, so it's like a sheet. It's like pouring paint on a sheet and checking the patterns, right? To try and figure out a formula. Anyway, so what I did was I figured out that, right? I got the diameter of one nebula. So what I did was I got different nebulae, right? And I started charting them. So this is the light years of a nebula. This is the expansion rate of the nebula, 19 kilometers per second. And then, excuse me, would it be better if I point with the mouse? Okay, this one is just this by this, okay? And then this is that multiplied by a constant. Now, why did I do that? This is the answer in years, right? So I got the answers right. Initially, what I did was I got the spreadsheet is intimidating. It's not that, it's all a repeat of the same thing. So basically what I did was I got the light years, I got the kilometers per second, I multiplied them together and I got this as an answer. Now this is different to what the answer should be, right? So I got this, but the answer should be this. So I figured out that the difference between this and this as a factor is this number, right? So I'll give you an example. Let's say that you go to the shop and you give the guy $5 and you get back 2 bottles of milk. Sorry. You go to the shop, you want to buy 2 bottles of milk, you give him $5, right? And you get back $1 in change. Okay, so in other words, you figured out that 2 bottles of milk is $4, which means that 1 bottle is $2, right? So that's what I'm doing. But what I did was I bought lots of different bottles of milk. So I bought a 3-bottle of milk combo. I bought the milk that's made by a Florida company. Then I bought the milk that's made by the California company, and I started charting them out and seeing if I could find a relationship between the prices, how many I bought, and which state. That's what I did. $1 for snakes. Oh yeah. So just to explain it again, right? I went to the same store over and over again, and I bought 2 bottles, I bought 3 bottles, I bought 5 bottles, I bought 1 bottle, and I also bought this California brand and the Florida brand. And then I tried to find a pattern. Now what I found was that the pattern was something I couldn't see initially. That's my research method as well. Awesome. Well, then you'll get exactly what I'm talking about. So this was the pattern. The pattern was these numbers. And I couldn't figure out what the pattern was. But I realized that the thing that it was related to was the expansion rate. So the expansion rate of the nebula was related to this constant. Because every time the expansion rate got smaller is the correct formula. Yes, well done. You are about 20 steps ahead of everybody, right? So what happens is, but my formula is actually easier to use, and I'll show you in a sec, right? So as you noticed, you are welcome. When the rate goes down, this difference in number goes up. When the rate goes up, the constant goes down. When it goes really high, the constant goes really low. So the first thing I figured was that the constant, this extra number, right, was inversely related to the expansion rate. So the faster the expansion rate, the lower the constant. All right, so that was the first thing I figured out. But then what I did was I checked whether it went down by the rate that the constant went up. So for example, you know, if the expansion rate of the nebula went from 13 kilometers per second to 26 kilometers per second, in other words, it doubled. If the expansion rate doubled, then the constant should halve, right? In other words, they work inversely to each other if it was a linear relationship, but it's not, okay? So what I mean, for example, I'll go back to the store with the milk. There is an emanation point to a possible temporal wave to our universe. There could be, but it's just speculation at this point. You never know. You know, the mathematics doesn't discount it for sure, but it'd be good. Imagine, maybe you could find it. I'll turn on the news one day. It'll be like Peterson discovers. It'll be hilarious. All right. So imagine that Booze goes to the store, because Booze's face is up here. She always gives me awesome stars, and so her face shows up. It's pretty cool. All right. So imagine Booze goes to the store to buy milk. Now, the more milk she buys, the more discount she gets, right? But it's not like, for example, if 2 bottles of milk, right, might cost $4, but 4 bottles of milk would be high quality down to almost plank time. Yeah, that's true. The 4 bottles, instead of paying $8, she's now paying $7. So what that means is that she's getting a bigger discount the more bottles she buys, right? So that doesn't match up one-to-one. It's not a one-to-one relationship. It's not like she gets a 10% discount all the time. So 10% of more bottles gives her a bigger price, but it's still 10%. No, the percentage is increasing. So Booze goes into the shop. If she buys 2 bottles, she gets like a 10% discount. But if she buys 5 bottles, she gets like a 20% discount. So it's a bigger discount than what it should be, because the shop owner really likes her and whatever. All right. So what I had to do was I had to figure out how big this discount was getting. And it turns out that it's related to the square root of the constant. So what I figured out was this extra number that kept coming up, right? When I square rooted it, square rooted it, it turns out that it went up by the exact rate that the expansion went down. So what that means is that this expansion went from 19 to 13, right? Hello from Sweden, lovely to see you. This constant went up by the same rate, right? So I knew by then that the constant was a constant squared. Okay, so I'll show you the formula that I came up with that is much simpler than the one that's given in the textbooks. Okay. What are you doing? Let's have a look at our friend here from Sweden. Rita, that is a Middle Eastern name. Rita from Sweden. Maybe you emigrated to Sweden. We are doing this formula here, my dear. Age of cluster in years equals, hey, Abdi Sheikh 77, equals the diameter in light years, that should be D, sorry. Okay. Diameter in light years multiplied by the kilometer per second rate of expansion multiplied by K squared. That's it. That's how simple the equation is, right? Now the question is, what is K? Hello. So K, right, equals this, 35.03245, okay, multiplied by 11 divided by the rate of expansion. So if the rate of expansion is 13 kilometers per second, then all I do is I get the K number, 35, times 11 divided by 13. And if the rate is 20, then it's 35 by 11 divided by 20. If the rate is 19, 35 by 11 divided by 19. So that's all. That's it. And then I was able to put that into Excel. And now look at this. Oh, that's a bot. It's one of the old original bots that Okay, so all I do is if I just plug in a number here, watch this. Let's just say the diameter in light years is 3, right? And the rate of expansion in miles. There you go. It changed it immediately. Age of cluster is 23,448 years old, right? That's how old it is. Just by plugging that in, it's done. So I built it, and that's all you have to do now. In miles, I would have to convert it. So what you would do, for example, kilometers per second, what you would do is you would put here miles per second, and I would convert it to kilometers per second in US. Yeah. So for example, what you would do is that's 19. So miles per second is going to equal that divided by 1.6. So it's going to be 11.875 miles per second. It gives you 19. And then all you have to do is copy this down and you'll get the same answer. Like it'll work it out all the way down. It's automatically working it out. So now we can see, for example, that 11 kilometers per second is 6.875 miles per second. 13 kilometers per second, 8.125. You are more than welcome, my dear. It's pretty good the way it's done. So I wish I could show you some of my mathematical modeling Excel spreadsheets. They were like gigantic because we were plotting like trajectories of populations of humans, and they reckon that we should go up to 9 billion and then stabilize and start to drop, but that really depends on how quickly we can advance the third world. We're doing very well as humans. We're doing amazingly well. All right, that's done. So now let's go to the next question. So nebula is 9 with 11. I'm just going to actually do the actual question, see if I'm right. So let's go 9 and 11. The answer is 121,500. I would love to see that. You would. 121,500 years old. Submit answer. Are we right? Did my formula work? Yes! Success, my friends. Okay. Next one. If one star has a temperature of 5,500 Kelvin, and another star has a temperature of 7,800, how much more energy per second will the hotter star radiate from each square meter on its surface? That is a formula I will have to teach you guys about later. What conditions produce a dark absorption line spectrum? Does anyone know? Goal! Does anyone know the answer to that one? Probably not. I will tell you the answer. What conditions produce a dark absorption line spectrum? Okay, and I will tell you. Okay. When light, we did this in a lecture like 2 weeks ago. When light from a continuous spectrum, right, passing through a cooler, low-density gas, it causes a dark spectrum line. So in other words, if you imagine if you get a globe, right, and you get an air conditioner, black hole. If you good try. Before the man a helicopter crash across the water 2017. Oh wow, you should scope that stuff. I love hearing things like that. That's pretty cool. Yeah, that's a very interesting thing, because you'd have to go through so many variables and cancel out and come up with hypotheses, and that'd be very awesome. A lot of space physics is theoretical. I would submit science as theoretical once. I would say science is hypothetical, and then you try to disprove a hypothesis, and if you can't and it's able to predict, then it becomes a theory. So yeah, I would say you're dead on. Yeah, so you get like a torch, right? Not a torch. Get like a bulb, a light bulb. Thomas Edison light bulb, and then get an air conditioner in front of the bulb and cool the air in front, and then shine the light through the cool air. And you'll actually on the other side on a piece of paper get a spectrum. Someone should try it if you can. Okay, so the answer is light from a spectrum going through lower density gas. I'm going to check my answers anyway. Turn on its head, nothing is perfect, not even science. That is exactly correct, my friend. And the beautiful thing about the true scientist is that they know that it's probably not completely true. That is the beauty of it. As opposed to dogma, which says we're true, whether we like it or not. And if you try to prove us wrong, it's you that's wrong. Science is fun because the goal is to make untrue facts. Okay, next. This figure shows the post-main sequence evolution of different stars in the HR diagram. When the sun leaves the main sequence to become a giant, what happens to its surface temperature and luminosity? Climate change is dogma for many scientists. I gave a lecture on that actually, on climate change, and we talk about consistency of events with the climate change hypothesis. So you can have a look. I think it was a 2 or 3 part lecture, so it was very good. But yes, I would say if someone holds it as a dogma, then they're not a scientist. They can call themselves a scientist, but they're definitely not one. Okay, so the sun, as it moves towards the end, its temperature increases and its luminosity should decrease. That should be correct. Let's see if I'm right. Submit answer. Let's see how we go. Am I right? Oh, I'm wrong. I am wrong. Why am I wrong? Maybe luminosity increases. Maybe I'm looking at the wrong thing. I got it wrong. All right. So when it becomes a red, blah, 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 blah. Let's go. Let's look up the book and see where I made the mistake. All right, you guys ready? Excuse me for a moment. I'm just trying to look it up in the book. What is the Boeing X-37B doing in space? Any thoughts? Oh, I can speculate if you like. But my idea is that they're trying to compete with the other smaller private companies which have already developed the hyperjets using the Scram engines that can sort of get from, Sydney to London in 4 hours. I reckon they're trying to compete with that. But I'm sure that there's always government programs that get involved. That's my thinking. I'd love to hear your thoughts though. What happens to its surface temperature? Damn it. I don't know. What happens to its surface temperature and its luminosity? Does anyone know? I'm trying to look it up in the book as we're talking. Damn it. I'm just going to type in luminosity. When the sun leaves the main sequence, what happens? Its luminosity increases and its surface temperature decreases. I got it the wrong way around. Defense component. I think DARPA and the Air Force are up to something. I would agree with that. I'm sure it is. It's military, the military which always advances our technology, right? Luminosity increases and the surface temperature decreases. Now, why did I get that wrong? That's interesting. Oh, you know why I got that wrong? Because luminosity works in negative numbers. Hundreds of billions of years. I didn't see what you said. Hundreds and hundreds of billions of years, eh? Could be. You never know. All right, did I get it right this time? I got it right this time. Excellent. All right, the next. Why do old supernova remnants emit X-rays? Yeah, it works in reverse. I know. I freaking forgot that, and I bloody gave that lecture like 2 weeks ago. Short-lived unstable isotopes. That was your last transmission. Why do old supernova remnants emit X-rays? Does anyone know? I think, from memory, it's because of the nickel. The expanding hot gas collides with the interstellar medium, is what the book says. There it is. The expanding hot gas collides with interstellar medium and creates X-rays. Are we right? Are we right? We are correct. Success. Okay. What eventually halts the slow contraction of a newly... How was iron made? Ooh, iron is made in the fusion in the star of a supernova. And it happens after carbon is made. They reckon that once the fusion gets so intense that it forces the carbon to fuse, it then goes up and creates almost all the other elements above that. So silicon, beryllium, carbon, all the other ones. We were just giving a lecture on that, I think, yesterday, and there's a map of it in the textbook. All right, what eventually halts the slow contraction of a newly forming star? I reckon it's the Coulomb barrier. No. Oh, nuclear fusion. Oh, nuclear fusion or the Coulomb barrier, I'm not sure. Crap. What eventually halts the slow contraction of a newly forming star? Nuclear fusion. Yeah, okay. So when a star explodes when iron is formed. During the supernova. It might be during the supernova. I'm not actually sure. I'm going to look it up actually right now. Lack of motivation. It would create a super unstable mass and fission into random atoms. You would think so. We're about to do that in quantum mechanics actually, the actual substructure of the particles. How is iron formed in stars? Let's find out. During a supernova, the star releases very large amounts of energy as well as neutrons, which allows elements heavier than iron to be produced. No, but iron is still formed during the fusion process. Actually, iron is the last one to form in the fusion process, and that's when the supernova then goes off after that. So there you go. Okay. What prevents neutron stars from contracting to a smaller size? I would say it's degenerate neutrons. I'm going to go with degenerate neutrons. What do you guys think? I'm going to tick it. I'm like 80% sure. Are we right? Yes! Correct. Thank you, Captain Deltron. Why will a helium flash never occur in some stars? Some stars have a hydrogen flash. No, some stars contain no helium. Some stars have a hydrogen flash in place of a helium flash. Some stars will never leave the main sequence. Some stars do not develop degenerate helium cores. I reckon it's degenerate helium cores. Correct. Oh, we found another bot. Gone. I love that. That's so much fun. You have no idea. Why will a helium flash never occur in some stars? That is crazy. You know how much energy they release? Like the helium flash happens inside the sun, inside a sun. And the flash emits like 10 to the 11. Like, what's that? That's like 100 billion times the light of a normal star in 1 second or something like that. It's crazy. Crazy stuff. All right, let's have a look. Why will a helium flash never occur? Because they do not develop degenerate helium cores. That's what I said. Ugh. You know how much pressure you need to make a helium core that's degenerate? So basically a helium core, if you squash it to the point where the actual atoms cannot be squashed any further, like they physically won't even exist, right? Then they become degenerate. So they turn into a force, even though it's a gas, it becomes tougher than steel. It becomes like Superman. Crazy stuff. And like 1 teaspoon of that material would weigh like more than all the Navy ships on the earth combined and stuff. It's just crazy stuff. Correct. All right. Next. Where in a star is energy 9% of organisms ever to live on the planet have gone extinct? Will humans be one? It's 99.9%, but you are right. Okay, show is pull out your dick and whack it. So Superman is degenerate. Yeah, I reckon humans will become extinct. Absolutely. There's no reason why we should remain. I mean, artificial intelligence. If a supernova doesn't kill us, or a meteor, or an asteroid, or the sun's expansion, or another, some sort of random climate change, or a volcano, or a famine, or wars, or interreligious strife, or, a virus. One of them is going to kill us. Artificial intelligence will kill us. Ernie Banks actually said yesterday, I tweeted it out. He said, artificial intelligence thinking to itself, why am I serving ants? Yeah. Drive is the game changer. Yeah. It's amazing that we've been around for this long, if you think about it. Where in a star's energy generated? I reckon the core. I'm going to say the core. How does energy get to the surface of the star? I reckon it is convection. I reckon it's convection. I don't know. I'm going to start with the core and see how I go. All right, I got one right. How does a star's energy get into space? Radiation. Am I right on the radiation? Yes! How does the energy get to the surface of the star? Yeah, it does have choices, yeah. Iron continues to fuse but absorbs energy, halting the balance, stating the obvious. You are my friend, but it's always a pleasure. It's good to have you back. When you state it, I feel more confident. So how does energy get to the surface? I would say it's either conduction or convection. It says conduction, convection, radiation. I would say it could either be conduction or convection, depending on the mass of the star. What was the plasma of the early universe composed of? I actually don't know. I don't think anyone knows. Why is it television for change? I pointed away from Earth. You say convection. Oh, okay, let's see. Oh, did I get it right? I got it right. It could be convection or conduction. All right. Now, the most massive stars use conduction or convection to get their energy to the surface. Who knows? I don't actually know. I'm going to look it up in the book. Me, conduction. Oh. Let's see. Conduction because convection is too slow. I think you guys know more than I do. So you say conduction. I'm trying to look it up in the book using Google. Most is radio from the conduction is not important. In massive stars, stellar structure. Okay, energy stars. They are conduction. The more massive stars, okay, let's have a look. Let's see who's right. All right. They are conduction, convection, radiation. It doesn't say blah, 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 blah. Doesn't bloody say. This is so annoying. I don't think it is. I think it's convection. Let's see who was right. Okay. The most massive stars. Damn. Why can't they just find me the answers? In massive stars, the core convection. It says that it's convection for the larger stars. Convection and conduction. Oh, here we go. Let's see. Are we right? I was completely wrong. You were right, bugger. Oh, they both use convection. Everyone was wrong. It was a trick question, the bastards. Oh, hold on. It's not convection. The most massive stars must use radiation then. Is that right? They must use radiation. That doesn't make any sense. I'm so confused. Ah, for massive stars, it's radiation. For small stars, it's convection. So then what uses conduction? Nothing. Ah, bugger. That means my freaking results. Do I still have a high distinction? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18. It's 18 out of 30. There, so take away that, so 18 is 20, 10, 12. So 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. All right, I'm still up at 95%. That's all right then. That's good. That solved that problem. Let's see. I think there's a couple more questions, then I can go. Finally. Oh, that's it. We're done. The closer an object approaches a singularity, the more violent the tidal forces. For which black hole are the tidal forces a greater concern? A small black hole or a large black hole? Yes, yeah, thank you. Well, it's with your help, I guess. Tidal forces are more of a concern in a small black hole or a large black hole? This one I actually do know. I know this one. Small black hole. Hey, look at you. Up the Aussies, Tassie and Melbourne. Hey, 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 hey. Tassie and Melbourne. Cool. All right, that was fun. I'm going to go now to my quantum mechanics. I think that will be next. Why? Because the difference between the gravity pull is magnified because it's such a short distance. So you got the event horizon's got small amount of gravity relative, and then the singularity is really close, so the gravity is huge. It goes through the roof, so you get this massive rip apart. Whereas the big one, it's so big that it's just a gradual increase. All right, all the best, guys. Facts don't care about your feelings.